All right, hi everyone. I'm really excited to be here to tell you about our work on Tower, which is a programming language and framework for implementing data structures that work correctly under quantum superposition. This is joint work with my advisor, Mike Carbin. So to give a little bit of motivation, the purpose of a lot of quantum programming is to realize the kind of algorithmic advantage that has been proposed by a lot of developments in quantum algorithms. So here on this slide, I put 3 examples of algorithms for problems such as element distinctness, subset sum, and closest pair. So these algorithms, in many cases, provide asymptotic, can be up to exponential speed up over the best known or the best achievable classical algorithm. So if you go and take a look at the implementations of these algorithms, you notice something interesting, which is at the heart of these algorithms here happens to be that they utilize a set data structure, right? A data structure in which you can insert elements, remove elements, test for membership of elements. And we want the operations of on the set to be efficient. By efficient, I'm going to generally mean polylogarithmic time. That's what's going to allow these algorithms to achieve their speed up. So to understand how on earth we can possibly have a notion of data structures that operate under superposition, first we have to talk about what quantum data is and how a quantum algorithm processes it. So if you think about classical integers, well, these are things like 0 and 1 and 100, or maybe 2 to the 32 minus 1, or something like that. The quantum integers are defined as all of the possible superpositions of these classical integers. So for example, the equal superposition of 0 and 1, or a superposition of the numbers 0, 1, and 100, or a superposition of all of the numbers between 0 and 2 to the 32 minus 1. These are all superpositions that are valid quantum integers. You can see one of the hallmarks of superposition is that in front of all of those numbers inside kets, you have this amplitude, which in general is a complex number that can have sign and have phase. So if we generalize the notion of quantum data to quantum data structures, then we can talk about things like lists that exist in superposition. So classical lists would be things like the empty list, or the singleton list containing 1, list containing 1, 2, 3, things like that. Quantum lists, by analogy, are superpositions of these guys. So the superposition of the empty list, list containing 1 and list containing 1, 2, 3, is a valid quantum list. How do we operate on these quantum lists? Well, you can take a classical operation. Here I've said push front, so we're adding an element onto the head of the list. And you can make such an operation work in superposition just by making it act uniformly on every individual classical list in that superposition. So far we've been talking relatively abstractly, right, just about the abstract idea of a data structure and what it can do. But how do we actually implement them on a physical computer? Well, how do we do it classically, right? So generally, we're probably relying on some sort of inductively defined data structure that is represented in hardware random access memory using pointer linking structures. And we manipulate these guys using recursive traversals of the data structure. So for example, you can implement the set containing 1, 2, 3, either using a linked list, which would give you linear time operations, or perhaps as a balanced binary tree, which might give you logarithmic time operations. So here's the problem. These proposals do not work on quantum computers for the kinds of quantum algorithms that we saw on slide 2. And I'm going to explain to you why. The reason is that when a data structure is expected to work in superposition inside a quantum algorithm, certain additional requirements have to hold compared to classical data structures. The first requirement is that all of the operations on the data structure have to be reversible. This means that for every operation, such as push front, let's say, it has to be able to operate either forward or backward. And it turns out that this property is necessary for data structure operation to preserve the superposition of the data. The next requirement is that the representation of the data structure has to be what is called history independent. And colloquially, what this means is that if you have a given semantic instance of the data structure, for example, the set 1, 2, 3, let's say, then there has to be a unique physical representation of this set in memory. it can't be possible to represent it in two different ways. And as we'll see, this is actually required for the algorithms we saw earlier to give correct results and to obtain the necessary speed. The third requirement is that all of the operations have to execute in time that is bounded by a classical rather than a quantum parameter. This is really necessary because we have to compile the programs for execution on the quantum architecture as a quantum circuit, and these quantum circuits have to be bounded in size. The problem that we identify in this work is that classical instances of data structures, the implementations like linked lists and hash tables, they don't satisfy these requirements. So we're going to need new implementations, and what's more, we don't have any existing tools, no languages or frameworks that allow us to make these quantum implementations. So in this work, we present three contributions that solve those problems. The first contribution is Tower, which is a quantum programming language that allows us to implement the sort of data structures we need. The next is Boson, which is a memory allocator that is invoked by Tower to ensure that these data structures are allocated in a history-independent way. And the third one is a case study, a library of data structures known as Ground, full of pre-implemented data structures that satisfy those requirements. I'll be talking more about how each of these contributions actually works, but briefly, the key idea behind Tower is that what we've provided is a set of programming primitives that are each reversible and can be compiled to a bounded size quantum circuit. In Boson, the key idea is that we achieve a history-independent representation of the data structure using the unique properties of quantum superposition. So let's talk about the first requirement. What is reversibility and why do we need it? So, while glossing over some of the details of the formalism, it's a fact that if you have data that is being stored in superposition inside the quantum computer, you can perform operations on this data that are either reversible or irreversible. Reversible operations generally preserve the superposition of data, whereas irreversible operations don't. So on the left side of the slide here, you see our previous example where we take a superposition of lists and we push the element 2 onto the front of each of the classical lists in the superposition. And you can see in some sense the superposition has been preserved. It's still in superposition after this operation. Now by contrast, something else you could do with a linked list that exists in superposition is you can measure it. So you can observe the quantum data. And when this happens, the linked list will collapse from superposition. So in this case, superposition of 2 and 2, 1 will collapse to one of those two classical lists with probability 50% each. This destroys the superposition, and if you think about it in the context of the algorithm, it ruins the speedup and causes the outputs of the algorithm to be incorrect. Now, what's the difference between the push front and the measure operation here? I'm going to argue that one big difference is that push front has a reverse. The reverse of push front is remove front, right? The operation that takes off the 2 from the head of the list. Whereas there is no reverse of the measurement operation. It doesn't make sense physically. So the key idea here that we're going to use in Tower is that we're going to guarantee that all of the primitive operations, including those that manipulate data structures in memory, are going to be reversible primitives. Let's see an example of how we're going to do that. So let's try to implement this push front function. And let's say we're calling it on this list L containing 1, 2, and we're trying to insert this element 6. We can execute the function forwards by prepending 6 to the front of L. So you can see this is a Tower function that accepts the arguments L and X. So what are we going to do here? First thing that we're going to do is we're going to allocate a new node that's going to store 6 and a pointer to the existing list. What we're going to do is invoke a set of reversible primitives, starting by swapping the values of L and the temporary variable head here. And we're going to prepare to store the pair 6 and pointer to the head of the list, store that in this temporary variable node. And at this particular point, we have a temporary variable called head that the program no longer needs. Now, there are more details in the paper about why specifically we chose this particular representation of the program and what we have to do here. But the point I want to point out is that because all of the primitives have to be reversible, a program cannot simply take a variable that it does not want or need and discard it from the memory. This, in the previous talk, we saw this was the property of linearity. So here, what you can do in Tower is you can invoke an operation called uncomputation, which some of you may be familiar with. It's an operation that reverses the computation that produced a value in order to reset its value back to 0. Now, a value that is 0 can then be safely discarded from the program, which we do next. Okay, so we're almost done. What we need to do here is we have that pair, 6 comma head of the list, and we're going to commit it into memory using this operation here that's a random memory access. Essentially, what the notation is intended to convey is that you're dereferencing the pointer L, and you're storing the value 6 comma that pointer into memory at this point. And now we just gotta uncompute this temporary variable node as well. And as you can see, we're done. At the end of the function, we have 6 comma 1 comma 2 in L. What's really nice about this is that now you automatically get the reverse implementation as well. So if we execute the function backwards, then we're supposed to remove 6 from the front of L. How do we do that? Well, we just execute every single step backwards because all of the operations are inherently reversible. And look, now we got back to where we started. So the takeaway from this example is that what Tower allows the developer to do is implement these reversible data structure operations. And it has some innovations over existing frameworks in that it gives you high-level data and pointer types, such as integers. And it has this operator for reversible memory access that encodes random access memory. Cool, so that's the first requirement. What about the second one? History independence. History independence is pretty hard to understand from a formal definition, so instead we're going to start with an example. So here, let's say that we have two sets, S1 and S2, and these variables are both supposed to mathematically denote the set of 1 comma 2, right, that abstract set. Now, it is a property of quantum mechanics then that we would expect to, if we were to place S1 and S2 into a superposition with each other, such that the signs on them are opposite, so the phases are opposite, then we expect this difference here to be 0. That is, they should cancel out. They should be as if they never existed. This property is called quantum interference. Specifically, it's the destructive variety. If you know anything about quantum, you've probably seen, like double slit experiment, that sort of idea. That's what's going on here. And it's one of the central phenomena that's being exploited by the quantum algorithms in order to give you, the speed up that you need. So this property is really essential for the algorithm to work. If the property of this thing equaling 0 does not hold, the algorithm breaks. Let's zoom in a little bit then on what it means for S1 and S2 to denote this set. How do we implement this set? What if we implemented sets using linked lists? Then a valid choice might be to say that S1 is represented concretely as the linked list 1 comma 2 and S2 concretely as 2 comma 1. But now you see the problem. Because if we do this, then their physical representations are actually different. Despite the fact that they denote the same abstract set, when you put them into the superposition, they don't give 0. They don't give this interference property. The result will be that the algorithm's output will be incorrect. Okay, so all right, we're going to have to fix that problem, right? We actually have to do something clever. In this case, maybe we say, we're going to enforce that the representation as a linked list has sorted and deduplicated contents. Right, it's probably the first thing you try to make the linked lists look exactly identical. And you'd think that this would work, but unfortunately, we're not quite out of the woods yet. Because if we dig a little bit deeper, we realize that there isn't one unique representation of the linked list 1 comma 2 either. If you actually think about how a linked list is laid out in memory, well, I have to talk about pointer addresses. And depending on how your memory allocator has chosen to arrange these guys in memory, you might have 2 different allocation structures for the same list. And this gives you the same outcome. The algorithm is still incorrect. Okay, so how can we possibly get ourselves out of this mess? The observation here is that we need a fundamentally deep property about the structure of the data structure. And that's called history independence. Now, history independence actually has a bit of a long history. It was first introduced in the context of privacy and security. And what it says is that you can have an abstract data structure that has a history-independent implementation, if and only if you have two equivalent instances of that data structure, equivalent meaning the same set of abstract operations produce them, then the physical representations of these two instances must also be identical in memory. Put it very shortly, this means that semantic equivalence of two data structures implies physical equality of those data structures. So this is the thing that we need. How do we actually achieve it? How do we take a linked list like this one and make it independent, history independent? The key idea behind our solution is we're going to exploit quantum superposition, right? Because quantum superpositions actually allow you to do this trick where you store the value of the set as the uniform superposition of all of the possible permutations of the linked list 1, 2 in memory. As you can see here, the result is that you're going to actually have that S1 and S2 are both semantically and physically equivalent. And this means that the output of the algorithm will finally be correct. You're probably wondering, how do we actually achieve this superposition representation? I mean, it's probably really expensive, right? Turns out that it's surprisingly not that expensive. We give the details in the paper, but there are strategies that are commonly used in quantum simulation algorithms that actually solve exactly this problem of taking a list of values and producing a uniform superposition over their permutations, which is very cool. In the paper, you'll also find an implementation of sets using radix trees rather than linked lists. So you can get that nice polylogarithmic time complexity rather than the linear time operations. Cool. So if you've been paying attention, you've noticed that we've covered the first two requirements here. The third requirement is going to be explained in the paper. I sadly don't have time to talk about it today. It's not as interesting as the other two. Briefly, what we do in Tower is we have a type system that classically bounds all of the possible recursion depths of the functions, which ensures that all of our functions can compile to bounded size quantum circuits. Okay, so we've talked so far about a lot of data structures in superposition, but we have not really actually given many examples of what these data structures look like. And that's what I'm going to try to do next by discussing the data structure library we implemented in Tower, which is called Ground. So there's a lot of stuff on the slide right here, and you don't really have to focus on all of it. I just want to point out that what we did in the Ground library was that we developed a set of data structures. These include lists, stacks, queues, strings, sets, and more that have been previously unexplored in the literature of quantum implementations, quantum programming languages. We showed that these data structures are actually able to satisfy the asymptotic complexity assumptions that state-of-the-art quantum algorithms are actually making. And if you look at the complexities, they're roughly in line with what you expect the classical versions of these data structures to have. And I'll point in particular to the fact that we have a polylogarithmic implementation of sets. How do we know that these complexities actually are going to hold out? Well, we verified them by compiling all of our Tower programs to quantum circuits. And we counted the number of qubits and gates that were required as part of the implementation. And we showed that, parameterized in terms of the number of elements as well as the system word size, we showed that the actual size of the circuits we get is in line with the asymptotic complexities we promise. So, this work really allows us to achieve the requirements laid out by quantum algorithms for the data structures. There's more in the paper that I don't have time to share with you today. So a big question is, if I have some classical understanding of how I implement a recursive data structure traversal, how might I convert such a function to a quantum one, say in a language like Tower? So a lot of problems actually arise when you try to directly do this. In the paper, we have a case study that describes 3 of these challenges and how we managed to resolve them during the implementation of the Ground library. Briefly, the first challenge is that if you have recursive structure in your data structure traversal, and you need to uncompute those recursive calls, this can sometimes cause an exponential slowdown in the efficiency of your function, which would be really bad. Other challenges are that uncomputing temporary values after you performed a lot of state mutation can be very tricky because the state has changed by the time you want to uncompute a value. And the third challenge, it's quite weird. It's the fact that if you want to compute the time complexity of a quantum program, you have to do this weird thing where you sum up the complexities of the different branches in your program rather than taking their maximum as you might on a classical computer. Yeah, the details here will be in the paper, and I'd be happy to chat with you about them. We have solutions proposed. So just a quick recap, in this work, we provide 3 contributions: Tower, a language for data structures; Boson, a memory allocator guaranteeing history independence; and Ground, in which we use Tower and Boson to implement one of the first quantum libraries of data structures. You can find our full preprint of our work on arXiv. You can also get our artifact on GitHub, start playing with it, implement your own Tower programs, see what kind of data structures you can implement. And I want to leave you on a parting message, which is that I really believe that quantum software can be understood if we apply the right sets of classical principles. They're not always the obvious ones. In this case, it's history independence, something that you wouldn't naturally have thought would have been connected. But in this case, using that concept allowed us to build a bridge to having really valuable abstractions like data structures that we can use to build the quantum software of tomorrow. So I would encourage all of us to try to find more of them.
All right, thank you, Charles. We have a lot of questions, and we're not going to be able to get to all of them, including a few online, but let's first take one or two in person.
So I like the idea with this random allocation, but I have one question about the allocator, because obviously the empty memory is not in the image of the allocator and of the operation that allocates, and the space is finite dimensional because otherwise you can't uniformly pick. So then it cannot be in isometry. So how do you get around that?
I'm sorry, could you clarify what you mean by it can't be in isometry here?
Well, there is no linear operation on a finite dimensional space that is not surjective, and that is an isometry. So it's not a reversible, the alloc cannot be a reversible operation.
Yeah, so let me try to answer that question by describing a bit of detail about how the allocator works. So the idea is that before the program runs, the state of the memory is a free list. So if you're aware of free list allocators, classically, it's like a bunch of blocks that link to each other, all of which have been unallocated to the program so far. And we allocate memory by taking a block off the free list and giving that to the program. So what we do before the program starts is we actually perform the symmetrization operation. We perform a uniform superposition of the free list so that it's like the uniform superposition of all possible free list structures. And then when it's time to allocate, we just pop the first list off of that free list, which of course what you'll end up getting is a superposition over a bunch of different pointers.
But what if the free list is empty?
Well, the free list won't be empty, right? We start with a QRAM of a given size, let's say m elements, so like the numbers 1 through m, and then we permute this list of elements at the very beginning.
But the operation is provably not an isometry. So
it sounds like we might be talking about different
well,
operations.
Let's do it offline.
I'd be happy to talk more offline. Yeah.
Thank you. Are you aware of any advantageous algorithms that can make use of these data structures?
Do you mean apart from the ones on slide 2? Those are the algorithms that utilize the set data structure to obtain some speed up, right?
All right, well, basically answers my question.
Okay.
Hi, this is very cool stuff, but there's one really basic thing I didn't understand, which was how do you represent a pointer? Like at the low level, what's a pointer?
Right, a pointer is just an integer, really. It's just a value that says, I want to access the 5th memory cell, then the value of the pointer is 5. It's exactly the way it would be classically.
Okay, thanks.
Okay, so I'll ask one of the questions from the audience, which is, if you suppose you have 3 sets in superposition, can you reduce over sets like computer union over them?
Oh, right. If you're talking about performing operations over different branches of the superposition, let's call them, then we don't support that directly. These algorithms that we mentioned here don't utilize that operation, but it is a very interesting direction, and I would say it's something we're very interested in pursuing.
Okay, great. Let's thank Charles again. Quick important note before we head out. If you have a poster and it's not up, please put it up as soon as you can. People at the desk should be able to help you. The poster session is at the end of next session, so we need your posters up if you're going to present them. Thanks.